Portunhol com sotaque uruguaio.
I'm going to speak Portuñol with this Uruguayan accent. First, I'd like to thank you for the invitation by Enel and Colombia Global Center. It's a great pleasure for me to be here in Brazil. I love the city. I'd like to stay here for a longer period. And the idea of this presentation is the following. We've been talking about climate change for a long time, and I still believe that we have a lot of confusion in this issue. And Guilherme was talking about that. I see people talking, but I don't see much action. So I wanted to provoke you so that we can think about being pragmatic in this topic of climate change. How to bring more actions to this topic. So, what is climate change? To think about climate change, we have to talk about greenhouse effect and global warming. So, this is a drawing on how it works in a greenhouse. I'm not able to use my pointer. Can you help me? But that's okay. So what's happening in this greenhouse? We have the solar rays, the solar beams, and it's heating the soil of the greenhouse. So this heat is emitted back to the top and is then passing through the ceiling, the glass ceiling, and instead of escaping outside, it's going to remain within the greenhouse. So within the greenhouse, the temperature is higher than outside. So this is the greenhouse effect within this greenhouse. So what's happening in this planet is the similar thing. You have this the ray beams heating the soil. The soil is then emitting heat, and when it's escaping from the atmosphere, it's finding this cover that is very similar to this glass ceiling in the greenhouse, and then the heat is coming back. So this is a natural effect. If it weren't for this greenhouse effect, today we would have 15 degrees less. So this natural greenhouse effect allows for life and on planet Earth. But what's been happening is that in the last 300 years, the human activity has increased the greenhouse gases. So it's similar to having a greenhouse with this thicker ceiling. You're able to trap more heat. What's important is not the temperature is rising slowly, but what's important that we have now this intensified hydrological cycle. So what is the conclusion of this first part in our presentation? The problem of climate change is an increase of greenhouse gases. There's no doubt about that. This is the problem. So what are the sources of greenhouse gases from the geographic standpoint? Here you see this chart showing the evolution of emissions of greenhouse gases in the world. And we have three regions: China, United States, and the European Union, which are responsible for 52% of the emissions. Where's South America? Within South America, we have Brazil, Mexico, Argentina, and compare what we have. That means that we For instance, Uruguay, a very small country, Brazil, a big country, that we don't have to do anything. No, everyone must do something. But we should remember this chart. I think Brazil has this wonderful opportunity with COP30. So, who is designing the climate agenda in the world? Europe, right? So, we have to think about that. Sources, human activities. What are the activities that are generating the most emissions of greenhouse gases? To simplify, 73% is energy. Land use, 12%. Industry, 6%. And 3/4 of the emissions of greenhouse gases come from fossil fuel. It's very important, everything that we do in different areas, but we can't forget that. It's very important. It's important not to be oblivious about that. This is very important. So, what is the conclusion? The most important thing for us to focus as forces is to reduce the greenhouse gas emissions. Brazil is an extraordinary example in the energy area. Guilherme was talking about that. Uruguay is also a great example. The energy matrix is mainly renewables in this country, almost 80%. For other countries, this is more complicated. We have countries in Africa which are very poor, and it's very hard for them, but we have to focus on these areas. We have a lot to do with waste management. And the other way to reduce emissions is to use carbon sequestration. I won't discuss a lot about that, but I'm going to be available during the Q&A session. But we have a lot of opportunities in the forest sector. We have different initiatives concerning engineering. In reality, the emissions from the last 300 years put the planet in such a state that even if today the greenhouse gases emissions were zero, the inertia of the previous emissions would cause climate to change for 40 to 50 years. Sadly, the emissions won't be zero tomorrow. So we have this urgent need to improve the capacity to adapt, improving our resilience, diminishing our vulnerability. So as decision makers, we have to work a lot and increasing adaptation, reducing vulnerabilities. So what should we adapt to? How's going to be the climate in the future? We have the scientific community to answer this question. We have climate models. The climate models take the planet, divide it in several parts, and for each part we have several layers for the atmosphere, for the soil, and we observe the exchange of energy, heat, and so on. As everything we have in science, we have a lot to improve with these climate models. It's a very complex area with a lot of chaos, complicated physics. Just to give you an example, this is a chart showing abnormalities in rainfall during the summertime in the southeast of South America. What we've observed during the last century, the 20th century. And how was the evolution and rainfall observed in during the summertime with these models? We have 10 to 15 models. So this pink range is including the different outcomes from different models. So what happened in reality was that the models were saying that during the 20th century, the average rainfall would increase 5% per month, but the reality is totally different. This is a model simulating the present and the history. They are not trying to predict the future. So this is an example of the models not working very well. We have other places in the world where it works much better. It's science that is improving. So this is the first limitation with our use of models. And the second limitation that is even more important is that in order to use these models and try to forecast what's going to happen with climate in year 2080, we must imagine what's going to happen to the energy sources in the next 80 years in terms of population, deforestation rates, technologies. It's very hard. Try to imagine technologies within 30 years. It's quite complicated, very difficult. So what did the community do, the scientific community do? We proposed different scenarios of economic transitions, some very pessimistic, other very optimistic. Pessimistic is that the population is going to grow a lot and the fossil fuel is going to be the main energy source. And the pessimistic is the opposite scenario. And with the possible scenarios, we can connect them to the climate models, and then we're able to generate this future scenario. So that's what we've been receiving from IPCC. What kind of information we are receiving? Let's observe this window in South America with Argentina, Uruguay, and a region from Brazil, Peru. For this big window, once you connect possible socioeconomic scenarios to this climate model, in order to forecast what's going to happen to temperature, that's what we are going to have. In blue, the most optimistic outcomes. In red, the most pessimistic ones. So what are we saying? That at the end of the 21st century, the average temperature is going to be between this range of 0.5 degrees hotter and 6 degrees hotter. So if you're working with economy and you're interested in this exchange rate, you may say euro must be 30 cents and dollar $4. So what do you do with that? It's impossible. Is it useful? Not, right? It's not, right? And this is a great window, right?
People are never interested in those big gaps or windows. They're interested in a local community or a city or a state. When you have these projections at this level of resolution, the uncertainty becomes a lot stronger. This is for temperature. For rainfall, it's even worse. For rainfall, it is not very clear if we have a trend. So this is the state-of-the-art science that is projecting the climate for the future. We know that the temperature is going to increase. We don't know by how much. We know that rainfall will possibly more variable, but it's very difficult to forecast in the geographical scale that we need to. So what is the reality and what has been the reality in the last 30 years since we started talking about climate change? We discussed that we have to have people working with public policies well informed for planning. So you can ask the scientific community, how is the rainfall going to be 50 years from now, and how temperature is going to be 50 years from now? The scientific community already has answered this question the best way that they could. So for example, here we have an instance from Brazil. The question in this scientific paper is, what is going to happen to the eucalyptus plantations if the world becomes 1.5 to 2 degrees warmer? So they gathered data from evapotranspiration in South America, regions of South America with water deficit. This is historical. This is the observed changes, pre-industrial changes and current changes. So if you look with a lot of attention, you're going to find some change. There's not a lot, but there is some change. And after that, they included the same models that they used to estimate evapotranspiration, water deficit, and water surplus, compared to scenarios with 1.5 to 2% degrees higher in temperature. And here we can see how evapotranspiration changes and how water deficit changes or water surplus changes. So they conclude that for Paraguay, the water deficit will increase in 400 millimeters. Do you believe that? Where is the uncertainty in the models? Where is this number? We have produced this kind of information for 30 years. What is the robustness of these projections? And what is the conclusion we can get to? The climate change scenarios for the future by IPCC, the most respectable scientific community in climate science, are uncertain, inevitably uncertain. And I have been a part of IPCC since it started. This is how old I am. The objective of the scenarios by IPCC were not to connect to hydrological models or the level of malaria in a country, but it was to draw attention of the world. And their message was, if we follow those development models that we have been following so far, we're going to have a problem. It is the most common source of information for the governments, the national, local governments. By forgetting this uncertainty, it is not only about it being scientifically wrong, it is also dangerous to neglect the uncertainty. Through this message, it's a lot easier to understand, because it's a message that talks about uncertainties and not knowing if the models work 100%. So what has happened, as Guilherme mentioned, what has happened is giving the decision makers information for 50 to 60 years in the future. And you have uncertainties in that information. It is the best way to ensure that they will not act on it, because it is a very far deadline. And there are also uncertainties on top of that. So it's very common that they don't do anything, they don't act on that information. First, we have to understand that the climate changes in different scales. It's not only overnight or from one century to another. An example is Africa, and to the south of the Saharan Desert. This blue line is the rainfall observed every year since 1900s to a few years ago. The first question that we can ask is, in Sahel, did we have long-term climate change? Yes, we did. It is raining 180 millimeters less than 100 years ago. But you can see that there are major oscillations. There are decades with more rainfall and decades with less rainfall. That's what we call the decadal variability of climate. They do have decadal variability. In the 1960s, for example, we had a peak in rainfall and very little rainfall in the 1980s. We also have the variability from one year to another. This explains up to 300 millimeters of difference from one year to the next. So climate varies in different scales: days, weeks, months, years, decades. And what is the relative importance of that variability? If I ask all over the world, from these three variabilities, what is the most important one and how much more important they are than the others? So I'm going to show you a world map demonstrating the importance of rainfall variability, the importance of climate change for each of the countries, the decadal variability, and the annual variability. And if you see green or yellow, this means that that is not very important to explain what happened in the last 100 years. If you see blue or purple, it seems that climate change is very important for those countries. So you can see that the trend for climate change is not a very strong importance. When we go to decadal variability, you can see some regions are red or yellow, and the interannual variability you can see on the last map. That is the most important metrics for countries. So does it make sense to plan by only looking at climate change? No, it doesn't. This is dangerous to only look at climate change. If you look at the Eastern Africa, like Kenya, for example, all the climate models say that at the end of the century, the rainfall is going to be higher than today. And there is a physical meaning to it. There's a physical explanation. But what has happened in the last 20 years is exactly the opposite. This means that the models are all wrong? No. Maybe that is what is happening. We have a decadal variability, and we have just entered the dry decade. If we only look at the climate change projections and we concentrate in the year 2080, we might be making inappropriate decisions for a direct future or a near future. What happened where I was born in Uruguay? 100 years of rain in a location in Uruguay during the summer, we had climate change, lots of climate change. The average rainfall increased 80%. It's a lot. But what happened every year? Interannual variability. This is what happened. We have 70 years of observed data separated into two groups of 35 years each, the first 35 and the second 35. In the first 35 years, how many times did the rain increase twofold? In the first 35 years, that happened 2 times. In the second 35 years, it happened 8 times. The summers are more humid. There's more rain. This is good for pasture. This is good for agriculture. How many times did the rain decrease? 3 times in relation to the expected levels. In the first group of 35 years, 3 times. In the second group of 35 years, 4 times. And what does it mean? There is more variability in rainfall than we expected. There are years with a lot of rainfall and years with very little rainfall, and that is what happens. That is the year-to-year variability. It's very important, especially because it is associated to more extreme climate events. This is important today, not for 2050. If there are more adverse climate events, the question is, what can we do today to improve adaptability to what the future might hold? How can we improve this adaptability today for us to be more resilient in the future? We can build resilience through different ways. I'm not going to describe them all to you. Each region has their own resilience techniques. In agriculture, we diversify, we irrigate when it's possible. We work on genetics to improve the resistance to droughts. This is true for any sector. And also work with uncertainties. Reduce the uncertainties as much as possible and whenever possible with good information. Good information in the necessary time frame. If Enel is planning an electrical grid, and I will give you an information about what happens to rainfall in 2070, how is it going to affect Enel's work? If Enel is trying to improve the problem of extreme events and I provide them with the data for the average rainfall in the next 10 years, that is not going to help them at all. We should start not with the scientific knowledge. We should start with a question, with a challenge. What is the challenge? And after we define the challenge, what is the necessary science that we need to address that challenge? So there is daily information, seasonal information like El Nino and La Nina every 3 months, and there are prognoses between the scale of days and months. It's called sub-seasonal. But we should start with the problem. We should start with the challenge and use the scientific information to try to address the challenge, not the opposite. And also, we should be aware that when faced by all of those risks, we have to be capable to manage a part of those risks. But there's another part of the risk that we cannot manage. This has to be a transfer responsibility. We should have financial instruments to transfer the risks that we are not able to manage. This is a little theoretical, but the concept is important. if you identify the probability of anything occurring, for example, damages to a city, that is the typical curve. There are a few years that are a disaster. In most years, nothing happens. There are some years that are favorable, but the first thing is we have to differentiate the types of risks. For example, I have a risk which is a storm or considerable rainfall that affects construction and the electrical grid, but it's nothing frightening. Some other years, as Guilherme described 2023, that it's a disaster. Actually, it's the first time that it happened in observed history. So how can we work with this? What actions do we need for each one of those segments of crisis? They all have a different action. For this more frequent and less severe risks, it is very important to have urban planning, alert systems, early warning systems.
Improving preparedness. We have a lot being done in Brazil. We have communities communicating with each other, and not all risks can be managed, and we must foresee that with safe financial instruments, bonds, and agriculture. This is also happening, and science is key, estimating these areas. Which risks are manageable and which are not, and they need financial instruments. And what's happening is with climate change, well, I'm going to show you this chart. We have the same drawing for rainfall. In a few years we have little rainfall, and in some years we have a lot of rainfall, and most of the years we have an intermediate rainfall. If climate change only affected the average rain, that's what was going to happen. We are going to have a higher mean with similar variance. So here with climate change, we are changing the mean, but we are also changing the variance. You have more frequent extreme events with drought and much more with wet ones. So this is the reality we have to face today. We must be prepared today. We must act today. Not in 2070, but today. So, just to summarize, the problem of climate change and global warming is a problem caused by greenhouse gas emissions. And what's key is to reduce the net emissions. This is key. And for that, almost 75% of the emissions come from fossil fuels. Let's not be distracted with the cows and trees. 75% come from fossil fuels. Now, the climate is going to go on changing. There's this inertia of past emissions, and there's this inertia of current emissions, so we must adapt. And climate varies at different temporal scales, so we are going to have information for different scales, temporal scales. For instance, sea level. This is a long-term planning. For instance, planning a grid for the next 20, 30 years, we must consider the decadal variability, improving also the management of disasters. We need that year to year. And a message to us for the scientific community is start with the challenge, start with this problem, start with the user question. Don't start with your own curiosity. It's very hard to know how the climate is going to behave in the future. We don't know how high the temperature is going to be, and we know that rainfall is very, very uncertain. But if you take the last information from IPCC, there's this indisputable scientific evidence. There's more frequency of extreme events that is causing more damage. We must focus on that. And how can we improve adaptation? We must think about today. We wasted time playing with different scenarios for 2080. The UN informs and reports they are full of different scenarios about rainfall in 2070, 2080. What is it for? It's very good to raise awareness, but the Minister of Agriculture from Kenya with this 2080 scenario, how to deal with that? We have to change that. What can we do today if we are going to improve the resilience and diminishing vulnerability, increasing adaptation today? We are going to end up with this more resilient society that is more prepared for the future. That's it. Thank you.